Hi, I'm David and I would like to present you our latest work called GACE. The characteristics of LiDAR data impose significant challenges for 3D object detection. Especially the highly variable point density and the sparsity of the data make this task complex. Due to the angular offset of the laser beams, the density is highly dependent on the distance to the sensor and can be altered by occlusions in the foreground. This often requires detecting objects based on very few data points, which is especially true for classes with smaller spatial dimensions, such as pedestrians and cyclists. For example, in the Waymo dataset, about 30% of all annotated pedestrians consist of less than merely 20 points. Detecting these sparsely sensed objects naturally leads to a large number of false positive detections at test time. For this reason, determining a meaningful confidence value for the detections is critical to find a trade-off between precision and recall. Geometric properties of the detected objects and relationships to neighboring objects are a valuable source of information when evaluating a detection. For example, if we consider this possible detection of a pedestrian, it is also difficult for humans to assess it without further information. However, if we also look at the surrounding objects, it becomes clear that this is a pedestrian crossing a street with a group of other pedestrians in front of stopped cars. In addition to these contextual properties, there are also simple instance-specific geometric properties that allow for a better evaluation of an object. For example, as shown in this figure, the position of a second model on the Waymo dataset for detecting a vehicle is highly dependent on the size of the object. Vehicle categories between passenger cars and heavy-duty vehicles are harder to detect, potentially because they are underrepresented in the dataset. Similarly, the viewing angle indicating from which side the vehicle is visible has a significant impact on the precision. Existing 3D object detection pipelines, including the confidence estimation approaches, were largely inspired by 2D image-based object recognition models. After extracting features over several levels in the backbone, they are merged into a common feature representation in the neck module. On this basis, box regression and confidence estimation are performed in separate branches. This is understandable in the 2D image case, since usually no useful geometric information can be derived from the detection properties. In the case of 3D object detection, however, this prevents the confidence estimation from exploiting this useful information shown before. Inspired by these observations, we present GACE, an intuitive and highly effective method to improve the confidence estimation of any black box detector using geometric information. Given a set of detections from the base detector, we explicitly use these neglected features to enhance the expressiveness of the confidence values. In the first step, instance-specific features such as the base detector score, the position and dimension, the relative heading angle, as well as low-level point statistics are transformed into a compact representation using an MLP. In order to evaluate the plausibility of a detection in a more holistic way, we use the geometric relations to the surrounding objects within a certain radius. The distance and direction to the neighbors, as well as the instance-specific features of the neighbors, are encoded using a shared weight MLP and then combined into a single representation using max pooling. Based on the concatenated instance-specific and contextual features, the new confidence value is then determined using a final MLP. In a detailed evaluation on the Waymo dataset, we show that for several state-of-the-art detection pipelines, adjusting the confidence scores using GACE leads to an increase in performance without exception. If we look at the different classes, the performance improvements are significantly higher for the classes of pedestrians and cyclists. Objects of these vulnerable road users contain significantly fewer 3D points, which leads to a higher number of false positives. Especially in these cases, our confidence enhancement method benefits from the additional geometric information. In the corresponding precision recall plots, the increase in precision is clearly visible. These gains are higher in regions of higher recall, which corresponds to the regions of lower confidence scores. To demonstrate the general applicability of GACE, we freeze a GACE model trained on detections from a second detector on Waymo and apply it directly to detections of a second detector on the Kitty dataset. This also leads to considerable performance improvements despite the distribution shift to a different dataset. Even more remarkably, significant performance gains are also obtained when the same GACE model is applied even to a different base detector. These results demonstrate the excellent generalization capability of GACE and the general validity of the geometric information regardless of the dataset. If you want to try GACE on your own detector, our code is publicly available. Thank you for your attention.